Hi, welcome. This is Andre-Nicolas from the Gemini Observatory. It is a pleasure to present to you my latest result on the clumping in the wind of Wolf-Rayet stars. Let me start right away with the result. So my result is that the line profile variability in Wolf-Rayet stars decreases when the temperature increases. So from that result, you see that Wolf-Rayet stars have spectra with lines that are variable, and that variability seems to have a link with the temperature. At least this is what we observe. But how did we get there, and what does it mean? Let's start with the definition of a Wolf-Rayet star. The classical definition is an evolved massive star, an evolved O-type star that had an initial mass of 20 solar masses or more. That star has the surface hidden by a dense wind, and that's very important. That wind, the Wolf-Rayet wind, is fast, hot, dense, and turbulent. The turbulence is clearly illustrated by this phenomenal picture from Hubble of the star WR124. Wolf-Rayet stars have a very characteristic spectrum dominated by strong and broad emission lines in strike contrast with the typical absorption lines we see in most of the star types. How do we form those strong and broad emission lines? Well, the answer is basically that those lines are formed in the wind. To understand how those lines are being formed and to make sure we're all on the same page for the rest of this presentation, let's simplify the picture of how we form the emission lines in Wolf-Rayet stars. So let's assume that the wind is smooth and homogeneous. We only keep the fact that this moon is moving away, expanding away, going away from the star. We are observing it from this position here, which is this white token I just added. And what we see is a spectrum that has the intensity in y-axis and the wavelength in x-axis. We'll be looking at a specific ion, and if we isolate an infinitesimal part of the wind where this ion is present, and this portion of wind is moving perpendicularly to the line of sight, what we see basically is an emission line, a delta emission at the central wavelength of the line. However, if we go at the same radius but at a different place where the wind is going away from the observer, this other infinitesimal part of the wind is now redshifted and will be at a wavelength that corresponds to the central wavelength plus the shift corresponding to the speed of the wind at that radius. Symmetrically, if we go on the other side and take part of the wind that is blue shifted, that gives this blue shifted line on the other extreme of this sweep of Doppler shifts at a given radius. At that radius, if we integrate across all the shell at that radius, we sum all those delta lines all together and we end up with a box. The width of the box is determined by the velocity of the wind at that radius, and the height is somehow related with the temperature. So let's explore other radii. If we're closer to the star, so a smaller radius, then it's hotter, so the box is higher, but the wind is slower, so the box is narrower. And inversely, if we go further away, then we have a faster velocity, so the box will be wider, but it's not as hot, so the box is smaller. And if we add all those infinitesimal shells together and we integrate across all where the ion emitting that line is present, then it's equivalent to adding all those small boxes all together to get the final profile of the emission line. So basically, the width of the line is somehow related to the range of velocities where the line has been emitted and the range of temperatures. Now let's go away from our perfectly smooth wind and let's add one place where it's more dense than the rest. That little clump will then translate into a little bump in our spectrum. That bump will be at the wavelength that corresponds to the velocity of the wind where this clump is present in the wind. And its width and intensity will depend on the density and the velocity range in that clump. But of course, reality is not that simple. If we go back to our more realistic picture of a Wolf-Rayet wind, we have a highly turbulent wind, and we cannot link one-to-one a bump to a clump. We have a wide range of clumps of different scales, at different places, at different velocities, with different motions. It's highly turbulent, and the whole profile, the whole distribution across the line is being distorted by this turbulent behavior of the wind. Now we see the link between the variability on the line profile of Wolf-Rayet stars and the clumping in their wind. Spectroscopic monitoring that would be intensive enough would allow us to follow the evolution of those bumps in the line with time, because this configuration of density of clumping is evolving as the wind is expanding. Having the luxury to sit on a star for a complete night during multiple nights allows us for a full characterization of the clumping in the wind. But if you cannot afford such time and you just want to have a rough idea of the amplitude of the variability, a few spectra are just enough, as long as they were taken long enough in time. So for instance, once per night, and ideally not all in the same week. That way you can get snapshots of the configuration of the clumping and have a rough idea of how big are those clumps on the line profiles. The result I shared with you at the beginning of my presentation is the result of 20 years of observation. Why that? Not because it takes that long to do that kind of monitoring, but basically it's because presenting this beautiful final result as an introduction is the best way to give you the impression that I really knew what I was doing. Basically, we were looking for many other things, and it's after a long time of observing those stars that we realized that there was a link between what we were observing and other fundamental parameters in the stars. For 20 years, we've been observing at l'Observatoire du Mont Mégantic, at Cerro Tololo, and at the Gemini observatories to gather at least 5, sometimes more spectra per star for 100 of galactic Wolf-Rayet stars. That way we could measure the amplitude of the line variability for all of those stars and play with the data. So this plot that you're seeing now, again, is basically saying that when you take 100 Wolf-Rayet stars at different temperatures, you see that the intensity of the variability you detect is decreasing with the temperature. But that's what you observe. What does it really mean? Such an observation is in contradiction with the expectations. The expectations are that the type of mechanism that drives the wind in Wolf-Rayet star is already turbulent by itself. So it doesn't need an external or a different mechanism to make things to boil, because the wind is already turbulent. But if that was true, if that was the only thing happening here, then we would not see a trend with temperature. All the winds would be more or less turbulent at different levels, but with no link with any fundamental parameters. So what is happening? There's one hypothesis that seems to be a very appealing solution to that. And it's the idea that at the surface of massive stars, where it should be radiative, there's, before you reach the surface, a convective zone, very thin, caused by an iron bump. Therefore, you should expect some boiling just at the surface, just when you expect the wind to start. And that convecting zone depends on temperature. Therefore, possibly when the temperature is high enough, the convection layer is high enough in the star, therefore unable to push as much wind upward as if it were deeper in the star. That's one possibility. Another one is that there's something we're missing in the puzzle. Maybe there's something with opacity, something with the way we look at the different spectral types of Wolf-Rayet that is giving us the impression of this general and fundamental relationship. So we leave that to brilliant people like Dr. Michel Couret, for instance, to think of what we just presented. And I hope this will lead to a breakthrough to understanding the origin of the clumping in the Wolf-Rayet stars. If not, at least I hope you enjoyed my presentation, and I really dearly hope we'll have the chance to meet again in person next time. Thank you very much.